Hi guys, I'm Sabarish Kumar. I have started a new YouTube channel, Edu Medu. Welcome you all to my YouTube channel. I have first did a video on transport of gases. It's my first video, so there may be many flaws. So please cooperate and adjust with it. Try to rectify it in the upcoming videos. Please like, share, comment so that it will help me to improve myself, and also subscribe my channel for the upcoming videos. I have shared the link to download my PPT in the description, and I also shared the feedback form in the description. So I request you all to fill the feedback form, those ever watches the video, so that it will help me. Thank you. Now we'll move into the topic transport of oxygen. Before learning about transport of oxygen, we need to know something. That is, what do you mean by respiration? Respiration is nothing but taking in oxygen and some process that undergoes in the body, and carbon dioxide is produced as a result of that, and that carbon dioxide is released outside. This process we do call it as respiration. So this respiration occurs in three phases, that is external respiration, transport of gases, and internal respiration. External respiration is nothing but absorbing oxygen from the atmosphere and giving out carbon dioxide to the same. This we do also call it as ventilation or breathing. Next process is transport of gases, that is oxygen and carbon dioxide is transported between the alveoli and blood and tissues. This process takes place. And internal respiration, this is also called as cellular respiration, which means cells and tissues take up oxygen and produce carbon dioxide as a result of metabolism. This we call it as internal respiration. These process, the respiration takes place in a specialized system, that is the respiratory system. This respiratory system is highly organized in higher phyla of kingdom Animalia, and we do have it. This respiratory system starts from the nostrils, and then it moves on through nasal cavity, then pharynx, larynx, trachea, and this trachea is bifurcated at the level of sternal angle opposite the lower border of T4, and it is divided into primary bronchi. Primary bronchi is further divided into secondary bronchi, and this is divided into tertiary bronchi, which is further divided into lobar bronchi and two segmental bronchi and terminal bronchioles and respiratory bronchioles, and in turn at last it will lead to alveoli. This alveoli is the site which exchanges gases with the blood, that is oxygen will be given to the blood and carbon dioxide from the blood will be diffused into the alveoli. And this respiratory pathway is divided into two parts, that is conducting zone and exchange zone. What is conducting zone? The pathway that conducts the air, that is conducting zone. It starts from nostrils and ends at terminal bronchioles, and the remaining respiratory bronchioles and alveoli will constitute the exchange zone. We do have another specialized part, that is called respiratory membrane or respiratory unit. What it does? Nothing. The air in the alveoli is separated from the fluid in the blood cell capillaries by two wall layers, that is capillary wall layer and alveolar wall layer. These two wall layers in combination with their fused basement membrane form the respiratory membrane. We do call it as respiratory unit. This should be very thin, of the size of 0.3 to 1 micron with average of 0.5 microns. If there is thickness of either one of the membrane or any fluid accumulation between the two wall layers, then exchange of gases become difficult. So this should be maintained in a proper way to make the exchange of gases easier. So these gases which has to be transported and exchanged and conducted obey certain laws and has certain properties. We will see what laws it obey. As everyone know, the gases obey Boyle's law, Charles' law, Avogadro's law, and they also come up with the equation, ideal gas equation, PV is equal to nRT. But to deal with this transport of oxygen, we must be familiar with two laws, Dalton's law and Henry's law. What is Dalton's law statement? Yes, as everyone knows, the statement is nothing but total pressure exerted by all the gases present in the liquid is the sum of the partial pressure exerted by the individual gas in the fluid. So, what is this partial pressure? Partial pressure is nothing but pressure exerted by one particular gas in a mixture of gases. So, like that we have to calculate partial pressure of different gases present in an environment, and when we add it up we will get the total pressure of the gases. So, this is what Dalton's law states, and Henry's law states that solubility of gas in a liquid is directly proportional to the partial pressure. So, this gives the solubility of gas in a liquid, which is highly important. As oxygen is transported through the blood, we must know solubility of gas in a liquid. Okay, now we will see how it is transported. Before transportation of oxygen, the gas should be taken inside the lungs, which means the gas should be inhaled, so that only it can be transported. So, this process of inhaling is called inspiration. This inspiration is an active process, and during inspiration what happens? The chest wall or the volume of the thoracic cavity will be increased. So, because of this increase in volume, pressure inside the thoracic cavity will fall. So, when the pressure gets decreased, a partial pressure gradient will be set up between the respiratory system and the external environment, so that air can be taken inside. The air that is taken through the respiratory pathway reaches the alveoli. So, now we have air at two places, one in the external environment and the alveolar part. So, there should be some difference of pressure, partial pressure of gases in the inspired air as well as in the alveolar air. We will see what is the difference, and we will also see the significance of it. So, difference between alveolar and atmospheric air. So, partial pressure of oxygen is negligible difference, only 2 millimeter of mercury. But see oxygen. Oxygen has partial pressure of 159 millimeter mercury in the atmosphere, but only 104 millimeter mercury in the alveoli. Because of this huge difference, air is taken in. Air rich in oxygen will be taken inside. Carbon dioxide has very low partial pressure outside and high partial pressure inside. So, carbon dioxide rich air will be exhaled. This is the principle behind inhalation of oxygen and exhalation of carbon dioxide. Now, air is inhaled. Air enters the body, then the blood, after the blood it comes to the alveoli, then it comes out. This is the process. So, there will be a difference in partial pressure, which means partial pressure will be different at different levels. So, we will see how it is different, and we will also see what is the significance of it. So, in the inspired air, the partial pressure, as I already said, it is 158 millimeter of mercury, and in the alveoli it is about 104 millimeter of mercury. In the arterial blood it is about 100 millimeter of mercury. In the venous blood it is about 40 millimeter of mercury, and in the expired air it is about 116 millimeter of mercury. So, what is the difference? So, what is the significance of this difference? Is because of the lesser partial pressure of oxygen in the alveoli, oxygen can be taken in, that is here, and from the alveolar air is transported through the RBC into the arteries, transported through the pulmonary vein to the left ventricle, left atrium, then left ventricle. From the left ventricle it is taken to the arteries. Here no exchange takes place, just the gas is transported. But why there is a pressure difference? Because when the air in the alveoli is transported, what happens? Bronchial veins present in the lungs form a collateral circulation with pulmonary veins, so that some impurities will enter the pulmonary vein. Because of this only, partial pressure of oxygen in the arterial blood is bit less than the alveolar air. And venous blood, as arterial blood passes through the body tissues, they will give up oxygen to different tissues, and these will be converted into carbon dioxide, so that when the blood returns through the veins, the partial pressure of oxygen will be reduced. Okay, this is the significance of partial pressure of oxygen at different levels. So now how much amount of inspired air will be how much amount of oxygen and inspired air will be taken up by the blood, and how much amount taken up by the blood will be taken up by the tissues. There lies the question. We will see it. For 100 ml of air we inspire, only 5 ml of air will be taken by the blood. For 100 ml of arterial blood we take in, only 5 ml will be extracted by the tissues. So now this arterial PO2 is 98 to 100 and it does not change during exercise. But during heavy exercise or severe moderate exercise, what happens? The oxygen amount required by the muscles will be increased, so that they take in larger amount of oxygen. So when the blood returns through the veins, the partial pressure of oxygen will be reduced. So during venous return, partial pressure is reduced. In severe exercise, it reduces from 40 to 15 millimeter mercury, and in moderate exercise, it reduces from 40 to 25 millimeter of mercury. So this is the significance of partial pressure at different stages in the body. Now we will see what happens and how this oxygen is transported to the tissues. It is taken up by the blood. In the artery we have some partial pressure. Now how this arterial blood is transporting the oxygen to the tissues. It transports oxygen in two forms. One in dissolved with the plasma, another in combination with hemoglobin. So when it is dissolved, which means the oxygen must be soluble in the blood. This solubility is given by Henry's law. When the arterial PO2 is high, the amount of gas dissolved will also be high. When the PO2 is less, amount of gas dissolved is also less. In this form, only a little amount of oxygen can be transported, that is only 0.3 ml per 100 ml of blood per 100 millimeter mercury of mercury only it is transported. Only 3% of oxygen will be transported in this form. Remaining 97% of oxygen is transported only in combination with hemoglobin. Before seeing how it is transported in combination with hemoglobin, we should know something about hemoglobin. So, what is the structure of hemoglobin? Yes, hemoglobin has 4 heme groups and they are attached to the iron atom. This iron is in ferrous state. So, the valency will be 6. So, 4 will be balanced by 4 nitrogen atoms from different heme groups, and remaining 2, in that one valency is satisfied by the globin chain. Globin is a proteinaceous part. So, it contains amino acid pool. In that amino acid pool, nitrogen, one more nitrogen will be attaching this ion, and 6th valency will be free, because it is free to bind with oxygen and then transport it. This is the way by which hemoglobin is transporting the oxygen. Let us see what happens. There are different forms of hemoglobins. Here there are 4 chains. It is a tetramer. Hemoglobin is generally a tetramer. It has 4 chains. First one is alpha 1, alpha 2, beta 1, beta 2, which means 2 alpha and 2 beta chain. This is the normal hemoglobin chain of adults. But it has many variants. Hemoglobin variants are larger in number: HbS, HbM, HbC, and etc. So, 2 things we should know proper are HbA and HbF. HbA is adult hemoglobin. As I said, it has 2 alpha and 2 beta chains. HbF is fetal hemoglobin and it has 2 alpha and 2 gamma chains. And how it is transported? As I said, 6th valence bond of one iron atom combines with 1 mole of O2. So, there will be 4 moles of O2, then they combine with 1 mole of hemoglobin and they will form Hb4O8. This reaction, formation of Hb4O8, occurs in less than 0.01 second. And already we discussed 0.3 ml of O2 is transported by 100 ml of arterial blood in dissolved form. Now we will see how much amount of O2 will be transported in 100 ml of arterial blood in combination with hemoglobin. So normally in 100 ml of blood we will have 15 gram of hemoglobin. So 1 gram of hemoglobin can transport up to 1.39 ml of O2 in its pure state. Which means hemoglobin in pure state can transport 1.39 ml of O2. But due to presence of some impurities like methemoglobinemia, what happens? It can transport up to only 1.34 ml of O2. So totally 1.34 into 15 will give 20.1. So in 100 ml of arterial blood, 20.1 ml of O2 can be transported. So this is larger amount and it constitutes about 97% of transport of oxygen to the body tissues. Now we will see how we can estimate the which means combination of hemoglobin with oxygen. It can be assessed by a curve, oxyhemoglobin dissociation curve. What is this curve? The curve is nothing but we are plotting the partial pressure of oxygen against its oxygen saturation with hemoglobin. At a particular partial pressure, how much percentage hemoglobin is saturated with oxygen. When we plot it, we get a curve. The curve is sigmoidal in shape. The curve is sigmoidal in shape. Why the curve must be sigmoidal in shape? See, I'll explain you. See, here we have four groups, right? 4 ion atoms. So when the oxygen combines with the first ion atom, that is formation of HbO2, what happens here is it occurs in a very slow rate and there is no other stimulation, just binding alone will occur because the globin chain attached to the ion atom in a tense configuration. Because of the tense configuration, this reaction occurs in a slow rate. When the oxygen atom or molecule combines with iron, the tense configuration is changed to relaxed configuration. So that what happens is it stimulates the second oxygen atom to bind with the second iron atom, so that the reaction becomes fast. During that attachment to the third ion atom, the reaction becomes fast, and during the fourth atom, it becomes very fast and rapid. So this is the reason behind why the curve, ODC curve, is sigmoidal in shape, because of TR configuration, which means tense relaxed configuration of hemoglobin. So this curve has many deviations at different conditions. When the curve shifts to right, the oxyhemoglobin dissociation, which means oxygen binding with hemoglobin, is reduced. When it shifts towards the left, oxygen binding with hemoglobin can be increased. This curve that shifts towards the right during fall in blood pH and increase in temperature. Fall in blood pH denotes what? Acidity increases. When does acidity increases? When carbon dioxide is released into the blood. When carbon dioxide is released into the blood, they have more binding affinity towards hemoglobin. So oxygen binding with hemoglobin will be reduced and carbon dioxide will bind with hemoglobin. So that the curve will shift towards right. This has been explained by Bohr's effect. Loading of CO2 to blood causes unloading of O2, which means carbon dioxide binds to hemoglobin, so that oxygen binded with hemoglobin is released to the tissues. So this is what happens. Increase in temperature. When temperature increases also, oxygen binding with hemoglobin will be reduced. Increase in concentration of 2,3-DPG. 2,3-DPG is nothing but diphosphoglycerate. It is a byproduct, or what to say, it is an intermediate product of glycolysis. It occurs in the RBCs and it is formed during Rappaport-Lewis Behring cycle, which is a shunt pathway or bypass pathway of glycolysis. What this does? What is the importance of this compound? As you all know, it has higher affinity towards the beta chain of hemoglobin, so that oxygen carrying capacity of hemoglobin will be reduced. Oxygen carrying capacity of hemoglobin is reduced by the binding of 2,3-DPG to beta chain of hemoglobin, so that this curve will shift towards right. When the curve shifts towards right, the oxygen carrying capacity of hemoglobin will be reduced. So now, what are the factors that shift the ODC curve to the left? That we will see it. Carbon monoxide. Why do carbon monoxide shift the curve towards left? The reason is nothing but the carbon monoxide inhibits the formation of 2,3-DPG, inhibits the formation of 2,3-DPG, so that it can shift the ODC curve to left. HBF. How does HBF shift the curve towards left? Yes, as everyone knows, I said 2,3-DPG can bind with only beta chain of hemoglobin. As HBF do not have any beta chain, it has only gamma chain, it can increase the oxygen carrying capacity of hemoglobin, and by the way, decrease in body temperature. Okay. Now there is a term called myoglobin. Myoglobin is a monomer of hemoglobin, so that it can increase the oxygen. That means only one ion atom is there, so that it can easily bind with oxygen, and the curve is not even sigmoid in shape for myoglobin. It is a rectangular hyperbola for myoglobin. This is the hemoglobin curve and this is the myoglobin curve. Okay. Here I said HBF and HBA. When does this HBF gets transitioned to HBA? At the end of first year of age. Okay. Now 2,3-DPG, as I already explained, this is what 2,3-diphosphoglycerate is a substance made in the RBC, Rappaport-Lewis Behring cycle. It controls the movement of oxygen from the red blood cell to the body tissues. Now, what is the physiological significance of this curve? The curve has two parts. One is a flat part, another one is a steep part. Which means in the flat part, even when the partial pressure decreases from 100 to 80, only a negligible difference, the oxygen saturation will be reduced from 97.5 to 92.5. Not a huge difference, so this does not cause any defect during hypoxia. But during steep decrease, that is when the partial pressure of oxygen is decreased larger, from, for example, from 60 to 40, there is a huge difference in the oxygen saturation with hemoglobin. This is why people at high altitude suffers from hypoxia, where the at high altitude partial pressure of oxygen will be less and people will be suffering from hypoxia. And this is the physiological significance of this curve. Okay, now we will see one more factor which determines the oxygen carrying capacity of blood, that is P50. P50 is nothing but it is the partial pressure of oxygen at which the hemoglobin is half saturated with oxygen, that is P50. When the P50 is less, which means when in lower PO2, if the hemoglobin is half saturated with hemoglobin, then oxygen binding capacity of hemoglobin will be higher. If P50 is higher, then lower the affinity for hemoglobin for O2. This is what this means. P50 has an inverse relation with oxygen binding capacity of hemoglobin. Okay. Now we will see what are the vehicles of oxygen transport and what is the ideal vehicle for oxygen transport. Till now I said how oxygen is transported and in what forms they are transported. Now we will see what are the vehicles of oxygen transport. Vehicles are nothing but plasma, hemoglobin solutions and blood. So based on the ODC curve, we do say hemoglobin is the best or ideal transporter of oxygen. and this ends up how oxygen is transported. Now we have some other factors and terms which determines the carriage of oxygen in the blood and body tissues and in the lungs. First one, in the body tissues. During rest, what happens is 250 ml of oxygen is transported per minute to the body tissues, and that is what we express in the term called coefficient of oxygen utilization. Coefficient of oxygen utilization is equal to O2 taken by the tissues divided by O2 content of arterial blood. When we calculate, as we know every values, oxygen taken by the tissues will be 5 ml. When 20 ml is transported, only 5 ml will be taken. O2 content of arterial blood will be 20. So when we calculate it, we will be getting around 26%. And during activity, as there is increased carbon dioxide production, increase in H plus concentration, rise in body temperature, increased capillary density, this ODC curve will shift to right, and so oxygen carrying capacity will be decreased. In the lungs also, due to difference in partial pressure, the O2 will be transported from alveoli to the pulmonary veins. Okay, and this is how oxygen is transported from the atmosphere into the body tissues. That is what I explained. And one thing which I have to mention once again is, as we said, 15 gram of hemoglobin in 100 ml of blood can transport 20 ml of O2. As I said, if 100 ml of blood can be arterial blood is reaching the tissues, only 5 ml of air will be extracted by the tissues, so that only 5 ml of air will be absorbed, O2 will be absorbed from the 20 ml. Remaining 15 ml will reach the venous blood during rest. But during exercise, what happens? It increases 3 times. Oxygen requirement increases 3 times. So 15 ml will be reaching the tissues and only 5 ml will be reaching the venous blood. Now, what is the importance of learning this transport of oxygen? Because sometimes we do not get sufficient oxygen, sometimes we get no oxygen. These two conditions are noted as anoxia and hypoxia. Anoxia is complete absence of oxygen in the tissues. Hypoxia is lack of oxygen in the tissues. And this hypoxia may be due to different types. For example, if tissue is damaged, that is histotoxic hypoxia, and due to low partial pressure of oxygen at high altitude or deep sea, that is hypoxic hypoxia, and anemic hypoxia, red blood cell damage. Like this, we have different types of hypoxia. And what is the treatment? Treatment is only oxygen therapy. That is, there are different types of oxygen therapy using ventilator, invasive, non-invasive methods, and there is also hyperbaric oxygen therapy, which means giving oxygen at a higher pressure. That we can deal in the upcoming videos. And I hope this video will be useful for everyone. Please don't forget to like, subscribe, share and comment. Thank you. This is my first try. Please support me, guys. Thank you.